with the content.
This is how we do it. This is how we do it. La 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 la.
I'm Lina and we will be working out a fluid flow problem for you guys. Problem states, water having a density of 1,000 kilograms meters cubed is flowing at a rate of 1.85 meters per second in a 3.068 inch diameter horizontal pipe. At a pressure of 68.9 kilopascals, it then passes to a pipe having an inside diameter of 2.06 inches. Part A states, calculate the new pressure in a 2.067 inch pipe, assuming no friction loss.
So this is going to be our inlet and this is going to be the outlet of the pipe. These are our inlet conditions. And these are outlet conditions when you define our outlet velocity and our outlet pressure. And the problem states the density of the water, and then in the back of the book we found the viscosity of the water. So I'm going to start out with a mass balance. And in this equation, the density 1 and density 2 are equal to each other. So therefore, this will simplify to A1 V1 equals A2 V2. I will start out by finding each area. So area 1. This is our diameter. We divide that by 2 to get the radius. And if you plug that into the calculator, you get 7.39 inches squared. And then we're going to convert this to meters squared. And if you plug that into the calculator, you'll get 0.004769 meters squared. And then we'll do the same thing for area 2. And if you plug this into the calculator, you will get 3.36 inches squared. And then we'll also convert that to meters squared. Give 0.00216 meters squared. So now we found area 1 and area 2. From this, we can find velocity 2, the velocity of the outlet. And this comes from up here of our mass balance equation. And plugging in our areas that we found. If you plug this into the calculator, you will get 4.075 meters per second. And this is our outlet velocity. So now we're going to use this to find, well, we're going to find Reynolds number right now. So the equation for Reynolds number is the diameter times the density times the velocity divided by the viscosity. And we're going to use our inlet conditions. And that's converting our inches into meters. And if you plug this into the calculator, you'll get 61,967. So this is more than 21,000. It's is the criteria for a turbulent flow. So therefore the flow is turbulent. So now we've found both our areas and we verified that our flow is turbulent, so therefore that allows us to use Bernoulli equation. So Bernoulli equation states that Z1 times G plus V1 divided by 2, V1 is squared, plus the inlet pressure divided by density is equal to Z2G plus the outlet velocity squared divided by 2 plus the outlet pressure squared divided by density. And we're trying to find P2, this outlet pressure. So now I'm going to plug everything into the equation. Oh yeah, also these, since the height is the same at the inlet and the outlet, Z1 will equal Z2, which are both 0. So you can mark those out. So now I'll plug everything into the equation. Okay, so now we have everything known except for P2. So if we solve for P2, we get P2 equals 62.31 kilopascals. And that is our answer for part A.
We will be working on part B of the problem. Part B states, if the piping is vertical and the flow is upward, calculate the new pressure. The pressure tap for P2 is 0.457 meters above tap for P1. I'm going to begin by drawing a picture. Our diameter and velocity and pressure going in will all stay the same from part A, and so will our diameter out. Our Z1 will be 0 and our Z2 will be the height that was stated in the problem. Our V2 is what we calculated in part A, and our density is the same in the inlet and the outlet. So for part A, we set up a mass balance equation. The densities density 1 and 2 will equal each other, so they'll cancel out, and you're left with A1 V1 equals A2 V2. From there, we solved for A1 and A2 using the diameters we were given. From there, we were able to use this equation to solve for V2 when we plugged everything in. After that, we found the Reynolds number and saw that it was greater than 2,100 to make it turbulent flow. And this applies to part B also. Since it is turbulent flow, we can use Bernoulli's equation. So to start part B off, that's where I'm going to start. And since we stated back in our drawing that Z1 was 0, this part of the equation will be 0. From there, I will plug everything in that we calculated previously. Since we're solving for the new pressure, we will be solving for P2. And once you solve for P2, you get .81 kilopascals.
Thank you for watching our video today. I hope this presentation was helpful. I'd like to acknowledge Dr. Sangro and the University of Tennessee Chemical Engineering Department. Go Vols!